and thank you for the invitation. Hello. My name is Benoit, and I will talk today about one single thing, which is called the software supply chain. And it's very much related to what Derek, was it Derek? Derek Nunberg had to deal with. So he had to deal with this very big software supply chain that Pontus mentioned. So I will dig a little bit into this, give you some idea about what this is, and also what this means for people who care about the security of software applications. And also, I will very much support what Pontus has said. We need tools, and I will hint you at some tools that exist today to address these risks, as well as tools that will exist in the future, thanks to the research we're doing here. So as Rolf mentioned, I'm doing research in software engineering. That's what I do, so it means that my object of research is software, and I'm very much interested in how it's made and how to make it better. So security is an aspect, reliability is another. But I'm really interested in the process of making software. And the software supply chain is very much a result of how we make software today. So how do we make software today? We have a team. Nobody builds, Derek built a piece of software alone. A few people still do this, but most of us, we build software as teams. So we're a group of people, and we write source code, and we write different files and configuration files, and we write this pink thing that you see here on the left of the screen. And then on a very regular basis, we send these very precious things that we wrote into a gigantic pipeline of tools. So what happens here in the middle, this is phase number 2, is that the source code that teams write first get into something called a build system. So build system will be in charge of doing many things. The first thing it will do is that it will look at your source code, it will look at the different files that you have produced, and it will go on the internet and fetch all different pieces. So that's what Derek had to learn. He had to learn about all those different pieces, but first he had to reuse these different pieces. So it's called dependencies, libraries, packages, call it as you wish. And it comes from package registries, which are here. And these package registries are hosting pieces of software that are themselves built by other teams in other places in the world. And so the first thing you do is that you pass all your code and your scripts here into a build system that fetches those other pieces of code, glues them together, compiles them, analyzes them, tests them, do all sorts of things, and then eventually build a binary. If the build passes, you will get a binary, and then this binary will still go through a different number of other transformations. So you will put this into a container, and you will put a web server here, you will connect this to a database, and all these different pieces you will also fetch from other different registries, which are themselves fed by other people here, and then eventually you get this piece of software that you deliver to your users. So if you build a submarine, then you have a command and control system here, and you have submarine people here. If you build a mobile application, then you have the mobile application here, and you have your users here. Two things that I would like you to remember from this picture. The first thing is that Derek is here, FY developers are here, SAB developers are here, Google developers are here, and all of them, they deliver a product that's here. And all these people, they write and they spend a lot of time building the pink thing. But what they really deliver to their end user is composed of a lot of white thing. Actually, most of it is white. The pink is only a very small fraction here. Depending on how you count, depending on who you ask, the ratio of pink, so the thing that you own, that you have built, that you have written, that you maintain, And the ratio of white, so all these things that you fetch from different parties and that you integrate into your application, this ratio of pink and white, or your own code versus reused code, varies between 20 and 80 up to 5 and 95. So, and this is what you deliver to your users. I'm not talking about all the tools that you've used and that themselves have transformed all your code in order to produce this. So that's the essence of the software supply chain, is that what a company, a software company, like Saab, Ericsson, SAP, Google, delivers to their customers. They deliver a piece of software, and this piece of software is essentially made of software that they did not build themselves. Like Derek delivered a piece of software that analyzes PDF, but that was relying on many other components. So that's one thing. The software product is made essentially of code that was not written and maintained and shipped and analyzed by the company who sells you the code. And it was also transformed and analyzed and built by tools, software tools that are not yours. So that's the software supply chain. That's the first thing to remember, is that when you buy a piece of software, when you ship a piece of software, when you build a piece of software, at the end you essentially get something that it's not yours. It's not made by you. And the other thing that to remember is that those different pieces that have been assembled in this process in the middle themselves have been built by other teams. Sometimes these teams are other teams in your organization. So, for example, a big software industry in Stockholm, beyond bank and defense, is the gaming industry. And the big gaming industry, they're very, very big, and so they build a lot of these things themselves. So they build the game, but they also build the game engine, and so these teams here could be part of their own organization, a big organization. But most of the time, you build a piece of software, you focus on your feature, so you build a bank application, you build a submarine application, and you focus on submarine stuff, submarine code. And the things that you reuse are not yours. They're not made by your company, they're made by third parties. And so these developers are not in your organization, they're not in your country, they're not under your laws, they're not using the same processes as you, they're probably not using the same language. It's completely different. Nowadays, most of these people, they do open source. So there's a lot of open source here at the end. But the most important thing is that these people are not you. And you don't know who they are, and you don't control how they work, and you don't control what quality they provide. The only thing you can do is decide or not to reuse their piece of software. So those are the two things to remember. Essentially, what you have as a software application is not made by the people who provided you this piece of software. And the second thing is that most of it has been done by other people. So there's really multiple ways to look at it. One way is to say, well, do we really need all these things in the middle? And the question is probably not. There are things that could be avoided. Do we really need to reuse from other parties? The answer here is yes. You cannot build today a submarine or a web browser entirely from scratch. It's just impossible. As Pontus mentioned, the whole system is extremely complex. So just interacting with all the hardware, all the device, all the screens, it's just impossible. So you have to reuse. Reuse is a good thing. Modularity is also a good thing. So here what we see is that nowadays we are able to build software out of small pieces and assemble them automatically and stream this pipeline in a fully automated way. And this is good news. So reuse, modularity, automation, all of this is good news. The other way to look at it is that what you ship is essentially not your code. And so here maybe there is a risk that I will discuss a little bit later. So today we're here. Some of you know this by heart. Some of you here are on the left side of the screen all day long. This is what you do for a living. You build code, and you write configuration files, you build this code, and you ship it, and you deploy it. Some of you have never seen this. And for those of you who have never seen this, I would like you to give you a little bit of concrete hint of what that means. So for example, let's say that you're in the financial sector or in the art sector, and today you really wonder about all the hype around smart contracts. And so you're going to go there and you're going to see, okay, if I want to write smart contracts, I'm going to use this project here. Take it as an example. It could be any project, anything. This is the thing that was on the left side of the screen, right? People, so here we see 404 persons have written code, written files, written documentation, and have published all this stuff in this thing called a repository. Over the last years, 3,192 changes have been made to this code base. So this is what it is. So 3,000 commits, 400 developers, 22 stars, so 22 people who are looking at this, 22,000, sorry, 20,000 other projects that are reusing this project here. So this is what we see here. And we see this on a platform, online platform, which is called GitHub. So if you want to look at this, and if you want to maybe use this thing, or if you want even to contribute to this thing yourself, the thing you would do is that you would first get a copy of all this thing on your machine. So the way you would do this is that you would do something called git clone, and you would clone the entire thing that's online. So when you go online and you git clone, you really download all the code, all the documentation, and all the history of what is online. So all these 3,000 changes, you get them and you have them here on your machine. So this is it. So now you have a copy, a local copy. So I have a local copy on my machine of what those 400 people did on the left side of my slide previously. What I told you previously is that those 400 people, they write the pink thing, and then the next thing they do is that they reuse the many other things that are built by other people. The question is, you might wonder, how big is this reuse phenomenon? So the way we would do this is that we would go here, and I will go here, and we could look at something called, in the case of JavaScript, it's called the package.json. In the case of Rust, you would have a TOML file. In the case of Java, you would have a pom.xml. But in any case, those 400 people, they wrote code, and they also wrote something called a configuration file. So here they declare all the different pieces they need to reuse. So they reuse other modules made by their own organization here, but they reuse many other things for testing, for building, for analysis, for interacting with the environment. There are many different reasons you're going to reuse this. Some of you have heard about Log4Shell at the end of last year, so you're going to reuse a component to do logging. Yeah, there are many things you're going to reuse. So you see them here. The other question we can ask is, how much is this? So this is 42. Frankly, it's crazy, it's 42. I spent quite some time looking for a real product that had exactly 42 dependencies. And I told your colleague here, our colleague here, that there would be a 42. So there's 42. And it's a real number. So these 400 people, they decided, okay, we need exactly 42 components. No more, no less. Good. But these things, as I told you before, these things are themselves pieces of software. And the people who wrote Solidity AST, they also reused other components. So here we have 42, so we have OpenZeppelin, and the 400 developers of OpenZeppelin say, okay, we need 42 components. And the developers of each of these 42 components themselves said, okay, we need other components, and we need other components. So we have the direct dependencies. Here in this case, it's 42. And we have all these indirect dependencies. These indirect dependencies, they are, so we can look at them. They are, so if we go here, they're here. So this is all the dependencies of the dependencies of the dependencies. So there are many, many of them. If we ask JQ exactly how many there are, we get this number. So okay, so OpenZeppelin, a piece of code to write smart contracts, something quite sensitive. If you're going to put any kind of assets, I would put pieces of art, very valuable pieces of art. You might put other things like currencies. But so 400 developers, they need 42 direct dependencies. And what they really get is 1,119. Okay? So on the left side of my slide here, if I go back to the slide, on the left side here, we have people who write code. They write a lot of code, and they also write a lot of configuration files. And when they send this to the build system, the first thing that the build system does, I haven't compiled yet, I haven't executed that yet. I just went onto a package registry, and I fetched the 42 components that the 400 developers of OpenZeppelin said they really need. And I also fetched all the other components that the other components need and the other components need. And so eventually, I haven't started executing yet. I've downloaded 3,000 commits of OpenZeppelin, all the lines of code, as well as 1,000 components. And I'm just here at the very beginning of this. 1,000 components, probably developed by 10,000 people, who some of them wrote thousands of lines of code, some of them wrote one line of code, some of them wrote one line of documentation. But so this is, and we're just here at the very beginning. So I took the code of OpenZeppelin, and I'm just starting to see that it's going to go into a very, very big pipeline, and it's going to be mixed and analyzed and transformed and blended with many, many things until I get here and when I can actually use OpenZeppelin. So this is an introduction to the software supply chain and trying to give you a sense of what it is, and on a concrete example. You can redo this, git clone, and look at the different files, and you will get a sense on any system, except C++ that doesn't have a package manager, and that's too bad. So we're here. We essentially write a lot of code, and at the end, all this lot of code is blended with many, many other things. So why should you care? So as a software engineer, I love this. I think this is excellent because software reuse is a thing. It's been promoted since the 60s, and since the middle 2000s, it's really a thing. So it's a real success. But of course, it comes with a number of challenges. And the number of challenges for you here who really care about security, they really come from the fact that in this gigantic pipeline in the middle, many things can be compromised. So some people here can inject a vulnerability in this piece of code and then let it flow into your code. Some people a bit more patient and maybe greedy will go and try to inject something here. But this thing here is also a white piece of code. It's not yours. It's coming from elsewhere. So in the case of the demo I gave you, it was NPM. So in many of these places, things can go wrong, either bugs or ill-intentioned users. So for example, the first thing that can happen is that I download OpenZeppelin, I build OpenZeppelin, I run OpenZeppelin, but I also run those 1,000 other things. So all those downstream dependencies, very, very deep, like in the example of Pontus. So you have those different layers of software, and so very, very deep, and all of these are necessary. All of these components are going to be executed, and so you can, if you are interested in doing this, you can inject a vulnerability in one of these downstream packages. The thing with those downstream packages is that nobody knows about them. So it's very intriguing to go there. So for example, some years ago, there was this thing about event stream. So event stream, at the time, so this is a quite old story, a couple of years ago, but really at the time it was, people said we were imagining this would happen, but it happened. So really there was this, one of these 1,000 packages So in JavaScript, in anything, you're going to reuse many things. And so in this case, a malicious actor managed to compromise an open source package that was massively used by many, many different applications that run in a browser. And basically what this malicious actor managed to do is to inject in one of these components called event stream a piece of code that would actually hack into your smart wallet. So this one was very much related to cryptocurrencies also. And so cryptocurrencies attacks using the software supply chain, it's a big thing. There are stories approximately every week about this, but this was one of the earlier ones and the ones that's the most well understood. And so this was really based on the fact that any application has this dependencies of dependencies of dependencies of dependencies, and it's very hard for the developers of the application to really focus and find a bug in this one very, very deep. So you can infect a downstream dependency. This was also the case for Log4Shell in December last year. The other thing that you can do, much more difficult and much more rewarding, is that you can infect the build system. Because so when you infect event stream, you infect a package that's going to be on the developer's machine. So now I have the 1,000 packages on my machine, and if I really want, if I have the time and the resources, I can inspect all of them manually or with tools, and I have them, I look at them. But then eventually I'm going to pass this to the build system. So I'm going to go on with the process of testing and deploying and compiling in some languages. And so if you manage to infect the build system itself, you're deeper into this process of transforming the application. And so the very famous example that was all over the news 3 years ago now, or 2.5 years ago, so end of 2020, was SolarWinds. So SolarWinds, it was a software supply chain attack on the build system. So SolarWinds is a company, an American company. They build products, and at the time, the product that everybody was talking about is a product called Orion. And Orion is a solution that you as a company, you buy to monitor your network. So basically, this piece of software, you put it into your network, and it scans packets, it scans traffic. It looks for weird things, but basically, it sees everything that's on your network. If it's KDH, then it will see me downloading NPM packages. It will see emails. But if you are Microsoft, or if you are NSA, or if you are FBI, you also have a network, an internal network, and you also have a tool to monitor this network, and you buy it from an American company because you're an American administration, and you buy it from SolarWinds because it's a reputable one. And anyway, you buy it from SolarWinds. And so you buy a solution that's monitoring your network, and in your network are the deepest secret of your company. And if someone manages to inject a vulnerability into Orion, then this person can potentially leak many, many, many secrets. This is what happened at the end of 2020. And the way the attackers did it, because it was most probably a group funded by a state. The way they did it is that they injected the backdoor into the build system. So at the very, very end of the transformation of the code and the compilation and the optimization, at the very, very end, when nobody is looking at the code anymore because it's just about to become a binary that's going to be shipped, this is where they managed to hack into the system, introduce the vulnerability, and then let it flow. And then the Orion was infected, was shipped to the customers, and then on the customer's side, information was leaked. Very similar to what happened more locally here when all the Coop stores were closed in 2021. It was also the same kind of attack. So you can infect a dependency, you can infect the build system, you can also infect the package registry itself. So when you download packages, as I showed you before, the way you do it is that you specify, you write this, right? There's a human who writes this. One of the OpenZeppelin developers write art column 2.9.1. Ethereum.js -util. Humans write this, And humans, as we all make mistakes, we make typos. For example, I'm going to write graphlib, and I'm going to put lib instead of lib, I'm going to put ilb. I always do this. And you're going to do this. And if there is no graph ilb, then the build will fail. But if there is a graph ILB, the build will go on, and I will download graph ILB. And if a malicious actor put a package graph ILB instead of graphlib onto NPM, I will get this graph ILB, and then suddenly I get a package that's been uploaded on NPM by a malicious actor, and then I download the code, and I'm not aware of this because I'm looking at this and I see graphlib, graph ILB. From my point of view, it's all the same, and the build passes, and then I go on. So this kind of attack is called typo squatting. And nowadays, so PyPy is a package registry for Python. So Python is a pretty important language these days to do all sorts of data analytics and machine learning. And nowadays, so this is from February this year. Earlier this week, they decided to shut down, not to shut down PyPy, but to prevent uploading any new package, because there is this big attack where all these popular packages, some malicious actors have managed to publish on PyPy other packages which have almost the same name, but don't have the same name, and of course don't have the same code and don't have the same purpose. So those are very popular packages, and nowadays on PyPy you have hundreds of packages that almost have the same name. So you invert letters, you use upper and lowercase, you do all things, and then in this automatically built system, they will be injected in your code. So basically, you can infect, or you can take control over downstream dependencies. With much more resources, you might be able to get into the build system. You can infect the package registries. You can infect any place all over here. And then eventually, you don't attack directly the source code here, but you know that your vulnerability that you inject anywhere here is going to eventually end up there. So that's really the challenge, is that we're not talking about attacks or vulnerability or problems injected here. We're talking about problems injected anywhere here, which are going to end up there. And those are software supply chain attacks. So it's beautiful, it's modern, that's the way we do it. There are problems, and there are solutions that people are starting to investigate. The first one is called the software bill of materials. You might have heard of it because just after this very, very big SolarWinds incident, it was a very big thing in the US, it was a big thing in the world, but it was a big thing in the US. And just after that, there was a new president, and almost the first executive order from the White House was to say, okay, we need to do something about cybersecurity. And one of the things they said is that now we want all our providers to provide something called a software bills of material. So the software bills of material, it sounds pretty simple, is that you're giving me this. So I'm interested in, okay, you build the pink thing, but tell me everything that's white. That's the software bills of material. Tell me everything that's inside the application. I have colleagues here who love to take the analogy with food. On the food package, you know what you're buying, it's the brand, the thing, but you also have the list of ingredients. So give me this list of ingredients. In the case of software, it's called the software bills of material. It looks like this. So it's a big JSON file with the list of all the dependencies. I showed you before that for OpenZeppelin, I can have the list of dependencies. It happens that getting this list correct is not exactly easy. There are many things that make it difficult. One of them is that there's lots of redundancy in those big dependency trees. The other one is that you also wonder where you're going to do the snapshot. Do you do it at the very beginning, the way I did it, or do you do it at the end? Because the thing at the end has been transformed again. The other thing that is at the end is not only all the ingredients, but all the tools that you've used to blend these ingredients together. The build system, the test framework, the code analysis framework, all of these things. So it's not clear how to get this list and what to put in this list. But it's ongoing. here I cite not tools, but two standards which are emerging to document this list of ingredients. And tools are emerging, and they're slowly emerging because they're really in the middle of the mess, and they need to figure out how to do this. Another thing that you can do, and that companies do very frequently, is that they use tools to automatically update these dependencies. Because not only you have 1,000 dependencies in OpenZeppelin, but all of these dependencies are constantly evolving. As I said before, OpenZeppelin had 3,000 changes over the years. So for each of these changes, you have a new version. So it's not for each change, but in general, software evolves fast. When Pontus was telling the story of Derek, I was checking that the live coding demo I had prepared for today was working well. And then I had to update NPM. And then I had to update Node. And then I dropped out, and I'm using the backup now because these things evolve so fast. So you need to keep up to date. And when you have thousands of dependencies, you cannot do it manually. So you have bots. And so that's another solution that will help developers to face the challenges of the software supply chain. On GitHub, you have Dependabot. It's pretty famous. And then you also have another one which is called Renovate, which is for open source as well as closed source. A little bit of advertisement here. Renovate is done by a company called, is sold and distributed by a company called Men from Israel. But the lead developer of Renovate is here in Udenplan. So if you're interested, it's a good technology. And what it will do is that it will do exactly this. So it will tell you, look, for this package here, Nimbus DS, you're using 9.27, but there is a 9.28 available. And if I were you, I would do this change. And it suggests a change, and the only thing you have to do is accept the change. More advanced, people are looking at something called reproducible builds. So as I showed you before, this thing in the middle is pretty big. Many things happen here. And what happens is that even if you don't change the source code at the very beginning, if you press the button twice with the same version of the source code, it's very likely that you're going to have two binaries at the end, which are slightly different from each other. Which is a problem because you would like, if you, for the same version of the source, you press twice the build, you would like to have exactly bit-to-bit identical binaries. Why? Because if you had this property, then now, if you press the button twice and you don't have the same bit-to-bit identical binary, you know that something wrong happened in the middle. Nowadays, if you press the same button and you will have two different versions, you don't know if it's because of a problem in the middle or just because of some randomness in the build system. So this is becoming a big thing. It's very hard to do for many different reasons. In particular, because in the build system, you depend a lot on your environment. So you will have timestamps, for example. You will have temporary files which are created, which are with random names, etc. So all this randomness makes the fact that at the end, you don't have exactly the same binary, even though the source has not changed, even though nothing has changed. If you unplug from the internet and you rebuild twice, you will not have exactly the same binary. And that's a problem. People are working on this. In particular, Nix and Gix are two package managers which help you to do this. So instead of using NPM or Maven, or on top of these, you can use other tools. And Nix and Gix are two existing solutions. And here, again, is a paper that discusses this. The last solution I want to mention, and there are many others, but here I'm doing a selection. So there are many other solutions, but one I would like to mention, which is part of our research, is that, as I told you before, among those 1,000 dependencies of OpenZeppelin, it's very likely that many of them are not necessary. So the OpenZeppelin developers, they need 42 packages. And these packages need other packages, need other packages. But it's very likely that the OpenZeppelin developers don't need the very ones at the very deep in the chain, because they're needed by some intermediary packages. So the question is, how can we detect those unnecessary packages in the software supply chain and remove them safely? This notion of unnecessary code or unnecessary package is called bloat, and the operation of removing it is called dependency debloating. And so this is something that we've been working on a lot in the past 5 years in the context of the Java ecosystem. And so given a Java application like OpenZeppelin, give me this, and I will tell you, look, this dependency here, you can remove it from your configuration file, and everything will go fine. And the benefit of removing this one, which is a direct dependency, is that you also remove all the indirect dependencies. And removing code is good for many reasons. One is good because you're not going to be hacked on these packages, you don't get the bugs of these packages, you don't need to maintain those packages, and you reduce the size of your binary. So if you're going to ship binary on all the phones in this room, then you need less resources to do this, less resources on the phone, less resources on the internet. So it's a very good thing to reduce the size of the code. It's actually very hard because the code tends to be very much entangled, but it's also a very active research area, as well as a very important concern in industry. So in conclusion, I've introduced this concept of the software supply chain. I've given you a high-level description of what it can be in many, many different contexts. I've given you a very generic picture of this. I showed you an example. I told you it's excellent news. It's also potential risks. And then eventually I hint at different solutions that exist, different tools that exist that address different problems, as well as research papers. So for each of these points, there was a paper looking at it from an academic perspective. And with this, I would like to conclude my talk, and thank you.
All right, thanks very much. Are there any questions? We have about 5 minutes or so for questions. Yes, please.
Hi, can you hear me? Tomi Väisänen, Synopsys. Speaking of the SBOM, there's now this new vulnerability exchange, VEX. Have you heard of it? Do you have any insights of that as an addition to the SBOM?
I have not heard of it, I'm sorry.
Okay.
What is it?
It's a means to complement the pure SBOM with vulnerability data as well.
Okay.
It's been standardized as well, the same way as SBOM.
Yeah.
Any more questions? No. Maybe we should mention there's also a poster on this software bill of materials.
Yes, very much. So,
and so
I'm trying to see them. I'm sure they're
right.
here.
So during the break, you have a chance basically to talk to one of your students who is involved in this. Right?
Yeah. We have. So as I mentioned at the beginning, this work is supported by a project called Chains, which is an SSF project, and multiple colleagues in the room are part of this project.
All right. If there are no more questions. Oh, there's one more. Right. Sure.
Sorry, I have a bit of a sore throat today, but are there any similar regulations like the software bill of materials within EU pending?
So the question is there an EU regulation about the software bill of materials?
Legislation, will there be something similar like this software bill of material that was stated by the president of the US, as far as I understood?
Yeah, so I don't know of any similar order in the sense of the EU asking all its providers to provide an SBOM. Some countries are thinking about it. Right after the same order from the White House, there was also a big EU document warning about the risk of the software supply chain and documenting these attacks and these risks in a very detailed manner. But as far as regulation is concerned, I don't know of any document. I think today the main limitation is that nobody really knows what to put in an SBOM. If we look at the different, so I mentioned 3 kinds of attacks, so one in the dependencies, one in the package registry, and one in the build system. Today the SBOM is very much about the dependencies, but it says nothing about the package registry. It says nothing about the version of the packages registry. So have you used NPM? Have you used Yarn? Have you used OPAM? And it says nothing about the build system, which is also a very important thing because, for example, this SolarWinds attacks is for people interested in the theory. So there was this old paper called Trusting Trust, which basically says that you can put a Trojan in the compiler. And today in the SBOM, you don't have the compiler, even though it's a very important component. So nowadays, it's not clear what to put in an SBOM, so it's even less clear how to regulate the usage of SBOM.
Reflection on trusted trust. The problem was Ken Thompson pointed out in his Turing Award paper was actually solved about 2009 by David Wheeler from the Institute for Defense Analysis by double diverse compilation. And one of the things that it was pointing out is that there are other tools, including build tools, that could benefit from this double diverse build story. So I'm wondering if you heard of anyone actually doing it in practice, not just in theory.
So thank you very much for this question. It's a very good question. It's a very interesting technique. We are looking at it very carefully. We are pretty certain that nobody uses this in practice. Today, doing diverse double compilation with vanilla GCC, not a toy GCC, is extremely hard. We've never seen a paper or blog post about this. And again, the compiler is only a very small part. What we've heard about, though, is using multiple build pipelines. So after one of the actions that SolarWinds took, immediately after, well, a few months after the Orion incident, nowadays they build Orion with 3 different pipelines. The big difference with the diverse double compilation thing is that they don't have a bit-to-bit identical binary at the end. But they can still detect some inconsistencies, and they can still do some checks on the binaries that come out of these 3 different pipelines. So it's not as strict as the solution of David Wheeler, but it has inspired different solutions. The other people who are looking at this extremely seriously are Bitcoin, so the ones that communicate about it, because they have a lot of money at stake. And the last point about this is that we believe that someone very influential in order to put SBOM as high as the White House is David Wheeler, because he is the security counselor at the Linux Foundation, and he is involved in all those policy decisions. So we strongly believe that he is instrumental here. Yeah.
All right, last question. Yes.
No, it works. Okay. Good morning. Thanks for a very interesting presentation. Actually, I don't have a question, but I could do a remark on the question of if there is a EU legislation ongoing that requires SBOM, and the answer is yes.
Cool.
So I advise those who want to look into that to look on the text of the Cyber Resilience Act. It's being negotiated on the Swedish presidency right now. Thank you.
Thank you.
All right.
Thank you.
Then I would like to thank the speaker again. Thanks very much.